So in this video, we're going to use calculus to determine open intervals over which a function is either increasing or decreasing. And we're going to do it in the case when the derivative of the function has values of x for which it's undefined. So this problem says find the open intervals for which f of x equals x squared minus 4 all to the 2/3 is either increasing or decreasing. And what we want to remember is from the previous video, the first step in the process is to find the critical numbers for the function, because we utilize those critical numbers to establish our open intervals over which the function may be either increasing, decreasing, or perhaps even constant. And I've included the graph again as a visual aid, but again, if we're using calculus to determine increasing and decreasing functions, we actually don't need to see the graph. But being able to see and observe the graph does give us kind of an answer key for the problem and helps us to identify if we've made a mistake or not. So step one in the process is to find the critical numbers. And what I want to notice from the graph is there's going to be 3 of them. I have one spot here. It looks like at x equals 0, the derivative is equal to 0 because the slope of the tangent line is 0. But I'm going to get 2 more critical numbers out of this because the graph that I'm looking at has cusp at x equals -2 and 2. And we know that the derivative doesn't exist or is undefined when we have cusp. So places where the derivative isn't defined also gives us critical numbers for our original function. So I'm expecting to get 3 critical numbers, one for which the derivative is equal to 0, and 2 critical numbers at which the derivative is undefined. So step 1, find those critical numbers. And to do that, we need to take the function and find its derivative. So we're going to take f of x, which is equal to x squared minus 4 to the 2/3 power, and we want to find f prime of x. And this is going to be a chain rule problem because I have a function inside of another function. So first step is take the derivative of the outer function. So I'm going to bring the exponent down using the power rule. So we get 2/3 x squared minus 4, decrease that exponent by 1, so to the -1/3 power, times, and now multiply by the derivative of the inner function. So the derivative of x squared minus 4 is just 2x. So this is equal to 2 times 2 is 4/3 times, in the numerator I have an x, and I have a negative exponent here, which means I actually have an x squared minus 4 to the 1/3 in the denominator position. So let me see if I can make that exponent a little bit better. This is an x squared minus 4 to the positive 1/3 if I move this expression down into the denominator position. So the derivative is going to be 0. The derivative will be 0 when the numerator of the ratio is equal to 0. So when x equals 0, the numerator equals 0. We get a critical number because the derivative will be 0. But then I have to recognize I don't want division by 0. Division by 0 causes my derivative to be undefined. And the 1/3 power, the cube root of a function, is defined for any value of x. So the restriction that we have, so that we don't get a division by 0, the restriction we have is that x squared minus 4 for the derivative cannot be 0, or we get division by 0, because 0 to the 1/3 power would be 0, causing a division by 0 in the derivative. So now we figure out what are the values of x that cause division by 0 in the derivative. So add 4 to both sides. This was equal to 0. Add the 4 to both sides. Take the square root of both sides. So x cannot be, the square root of 4 is 2, but when we take the square root of both sides, we get plus or minus the result. So we get division by 0 in the derivative when x is plus or minus 2, and we get a derivative of 0 when x is equal to 0. So the critical numbers are going to be -2, 0, and +2. And I can see from the graph that I'm coming from -infinity up to that first critical number. So my open test intervals will be from negative infinity up to the first critical number, -2. And then the next test interval will be between the critical numbers -2 and 0. And then the next test interval will be between the next two critical numbers, 0 and 2. And then the final test interval will be my recognizing that once I get over 2, I'm going to infinity on the x-axis. So the last test interval is from 2 to infinity. So notice we have 3 critical numbers creating 4 open intervals over which the function may be increasing or decreasing. And then the next step is just like in the previous video, we need test values inside of the open interval that we can plug into the derivative to see whether the derivative is positive or negative. So for example, here I can say, hey, I see that x equals -3 is in the open interval from negative infinity to -2. I'm going to plug -3 into the derivative and determine whether the derivative on this open interval is positive or negative. So we're going to calculate f prime of -3. So plugging that into the derivative, we're going to get 4/3 times the numerator is x. So replace the x with the -3, parentheses, then -3 squared minus the 4 raised to the 1/3 power. And we don't need to approximate this number. We just need to know if it's positive or negative. So we work through simplifying it until we get to a point where we know whether we have a positive or negative number. So here I have -3 squared is 9. 9 minus 4 is 5. I have 5 to the 1/3. And right now I'm in a position to determine the sign of the number. 4/3 is a positive number, times -3 is a negative number, so positive times negative is negative, and 5 to the 1/3 power is a positive number. So I have positive times negative divided by positive is going to be a negative number. So the derivative is negative, which means my function is going to be decreasing on the open interval from negative infinity to 2. And when I look at the graph, as I move from negative infinity towards -2 on that open interval, I see that the graph is going down. The graph of f of x is going down. So indeed, the graphical evidence concurs with the derivative evidence that I have a decreasing function. Then you just step over to the next open interval. This is from -2 to 0. We need any x value in that open interval. So x equal to -1 will work. Plug -1 into the derivative, so f prime evaluated at -1 will equal 4/3 times x, but x is equal to -1 over square the -1 and then subtract 4 and raise it to the 1/3. So if we simplify this, we have 4/3 times -1 over -1 squared is 1. 1 minus 4 is -3. So we have -3 to the 1/3 power. And now I'm in a position to evaluate whether I have a positive or negative derivative. This is a positive number times a negative number divided by -3 to the 1/3 is negative. So positive times negative divided by negative is positive. So I have a positive number right here, which means my function f of x is an increasing function on the open interval from -2 to 0. So on the open interval from -2 to 0, I expect my function f of x to be going upwards as the outputs increase in size. The next test interval is 0 to 2. X equal to 1 is an element of that open interval. Plug 1 into the derivative, so f prime of 1 equals. The derivative is 4/3 times x in the numerator, so replace x with 1, and then it's x squared minus 4, all to the 1/3 power. Simplify enough to determine what the sign of the derivative is. 1 over 1 squared minus 4 is -3 to the 1/3 power. So I have a positive number times a positive number is a positive number divided by a negative number. Negative 3 to the 1/3 is negative. So the result is I have a negative derivative, which means the function is decreasing on the open interval from 0 to 2. And then I can look at the graphical evidence on the interval from 0 to 2. Does it look like the function outputs are going down or decreasing? And indeed it does. So the graphical evidence matches with the derivative evidence that we have here. So the final one, we have the open interval from 2 to infinity. 3 is in that open interval. Evaluate the derivative at 3, which will be 4/3 times x, but x is 3, divided by x squared minus 4, all to the 1/3, which is going to equal 4/3 times 3 over 9 minus 4 is 5 to the 1/3 power. So I have a positive times a positive divided by a positive is a positive number. The derivative is positive, which tells me the function f of x is increasing over the open interval from 2 to infinity. And when I look at the graphical evidence, I can see that once I get past the 2, moving towards infinity on the x-axis, that the function is indeed increasing.